Cool, excellent. Hi, everyone. As Krishna mentioned, I'm Dushyant, and I have the privilege of moderating this panel with this great set of panelists. As Krishna mentioned as well, keep asking your questions via Slido, which is also on the website. I think Vibha's walking around with a microphone as well for in-person questions, as well as raising your hand on Zoom. So really excited to hear everyone's thoughts on a couple of things. Maybe we can kick off with a fairly sort of broad question. So I think a few of you touched upon the fact in your talks that there is a sort of trade-off between, on the one hand, behavior priors and sort of more broadly just structure in RL on the one side, and the generality of a solution and its applicability to different tasks and different contexts. So what do you feel are the sort of structures and properties that behavior priors should exhibit to be general and transferable, and sort of where and how should we actually use them for this to be the case? Maybe I can start with Doina here.
That's a very interesting question, Dushyant. So there are some sort of general heuristics that have been used as priors, right? Entropy regularization is perhaps the prime example of that. I don't think so much of that, although those are definitely general and applicable under many circumstances. But I think there are situations where you have a domain and there are perhaps many tasks or many things that an agent could do in that broad domain. Then there may be useful behavior priors there, right? So if you have a particular robot, you might have lots of different reward functions that you want that robot to optimize. But in terms of, primitives for motion, for manipulation, for, attention, visual attention, and so on, those could be learned. And once they're learned, they could be reused. So that, to me, that is perhaps the most salient case.
Any other panelists want to offer a different view, a different structure that we should be using for priors?
Maybe I've got a complementary comment, which is that I do agree to a large extent with Doina that this is an interesting direction. I think one of the, maybe a point that we are reaching now is that we are actually able to study this scenario. Because I think until recently, especially for RL, this wasn't really possible because we didn't have the simulations that we could run at scale or the data that we collect in the real world at scale. And that's something that's beginning to change and is something that makes me, that I personally find exciting as an opportunity.
I think in addition to exploration, we also need some notion of, I don't have a word for it because I don't think it has been invented yet, at least not in RL. Some notion of what you would call fixed working memory, right? So people in representation learning worked on this idea of what is called, let's say, what can be thought of as slot attention, right? Which is basically taking something that is continuous and putting it into discrete bins. The bins are not pre-allocated. In that line of work, people have looked at discovery of or unsupervised discovery of entities. Some people call it concepts, some people call it objects, but you can call it entities in general. And so what RL needs, according to me, is some mechanism where we can have a dynamic state abstraction. You can implement this with attention. This is one way to do this. Like if you look at 5 or 6 years ago, people who started doing RL with CNN inputs, and they would plot these sort of heat maps moving around on the image. That was like a very early version of this. But I think a more structured version of this would be a combination of these, let's say, discrete abstractions. Of course, they can be learned through gradient descent, but they need to be, I think one thing that is missing is the ability to do dynamic allocation. So for example, in the current context of the task, these 7 objects are the thing that I need to care about. But as the task progresses, the abstraction changes. Like a very good example can be, let's say you're making salad, right? Initially, the onion, the lettuce, and then the cucumbers are separate things. But once they are in the bowl, the whole thing is just one unit, right? And you will use the memory to represent some other things. So I think fixed memory, with dynamic state abstractions is something that we need. And then we also need, this is something that also has come up in a lot of the work that has recently come up in what we have termed as egocentric AI, or not egocentric AI, sorry. This line of work which is doing navigation with RL. And one thing that we learned from that line of work was we need memory. So not just like working memory of attention over space, but also temporal memory, because almost everything we are interested in doing, at least in robotics, directly or indirectly will be a POM-DP. So you need some working memory to, well, remember things in state representations of like world maps, whether they are abstract or direct. Same goes for any sort of reasoning problems. So I think that we don't yet have those kind of abstractions in RL algorithms specifically. And one thing that I am very open to discussing about is in almost all of the works, we assume that Q learning or TD learning is the only mechanism to do this. That is a thing that I would like to question.
Yeah, I think as soon as you said this idea hasn't been invented yet, I started furiously taking notes, of course. No, but seriously, I think maybe to try and understand and paraphrase and delve into this a little bit, is your view that maybe, you know, some form of sparse attention over time, or just the knowledge that at each point in time, you will only need to call on a few different behaviors or a few different experiences from well in the past, or a few, you know, substates from your state itself. Is that the kind of prior information that you're talking about that we need to better incorporate in RL? Is that maybe a fair way to characterize it?
I think if you look at RL literature, there are two sublines or lines of work that have done something similar, but I believe some combination is needed. One is the whole line of state representation learning, which would be something very relevant to what you said. And then the other line is what you would say, learning options and using options, right? Basically hierarchical RL. But I think what we need to really think about is both of these things somehow separate time and space. Right? State representation learning is saying that it's attention over space, and I have working memory of some limited quantity, but the input is larger dimension, so I will have to use some mechanism of compression or focus. On the contrary, options give you temporal abstractions. I think you need a unified version of this, where spatiotemporal abstractions are simultaneously used. This ability to reason over space and time jointly is required. So let me give you an example. I think some people have looked at these frameworks. This is not my work, but I like that framing of the problem at least, is this idea of successor features, right? Which is basically saying that in some environments, you can essentially say the value function is modular in a sense. I think most of the works, at least the formalisms theory, presents linear combinations, but there's no particular requirement for them to be linear in a sense. The key sort of idea would be that value function is modular. But if you really look at the value function itself, it would combine both time, because you do value function computation through rollouts. So both time and space. So modularity would be like that. How would we implement that? I think that's an open question I don't know the answer to. And it seems that the current best answer is multi-head attention. Is that the final answer? I do not know.
Thanks. A lot of food for thought there as well. I'm wondering if any of the other panelists, Kelsey or Avi, have any thoughts on the structure of behavior priors that we should incorporate or shouldn't incorporate for generality.
Yeah, perhaps I've almost started having almost like a change of heart about whether priors are good in the first place for more and more general learning. Like priors are needed is the first thing that anyone learns in machine learning. You know, that's what I learned. That's what everyone else learned. But seeing what we've all seen in the last 2 years or so, it turns out it is it increasingly seems to be the case that a fairly general architecture, which has some like fairly minimal priors, almost no priors, once you point this architecture to a large enough data set, that gives you the best possible performance. And this goes against everyone's intuition. I don't know any, at least I'm not aware of any advancements in like, the theory of generalization in deep learning that like really explain why this happens, but at least empirically, it's, this technique is like unbeaten given a large enough data set. And of course, it has not really made a splash in robotics because we don't have access to those kinds of data sets so far. Like obviously, if you're in academia, you typically work with small data sets, but even for people working in industry, like, Google's not a robotics company, DeepMind's not a robotics company. So our data sets are also like small, arguably. They're not, they're not really like big enough to really like leverage transformer style models and get really good performance out of them. If like a robotics company crops up that's able to put 1 million robots in homes that do something, maybe not many things, but 1 or 2 things, and then you're able to like collect more and more data and sort of like increase the capabilities, and then that would sort of like provide you a pathway to sort of like increase the capabilities of these robots without using any behavior priors. I mean, as long as you're able to stay safe. And yeah, it seems to me like I at least based on what we know so far, I can't really think of like counters to that. So I would be curious to hear what others think about it and convince me otherwise.
I think Doina maybe has a response to that, and then I'm keen to hear from Kelsey as well.
I was wondering, whether we want to think of large data also as a prior, right? So in some sense, like you can think of, I don't know, the videos that are put by everybody on the internet as, that's a prior of what people do and, how they see the world and everything like that. And so in some sense, the distinction is a little bit fluid there, right? Like I can think of all of these data sets that you ingest in a large model as a non-parametric prior, or, I can think of putting some knowledge into a parametric prior, on the policy space or in the value function space. And in some sense, even when we decide what to train on, right, which of the available data to train on or how to generate data to train on, even that to me is a little bit of a prior. So just curious to hear how people are thinking about that.
Yeah, I think that's a super relevant point in terms of data being implicitly a form of prior as well. I'm also curious what other structure prior should have. Like Kelsey, you talked about physical reasoning as being pretty crucial to many of the many of the kind of examples that you showed, and certainly in tool use, I would think that you can't apply purely behavioral priors in a sense to repurpose something for use. So I'm curious how much you think physical priors are useful, and more broadly, what structure should priors have when we reuse them?
Yeah, no, thanks. And I really like Doina's point that data is a sort of prior. And I think that also hints at the importance of non-parametric priors generally. And I think tool use is actually, tool creation is a particularly good example of this because it changes the data you have access to, right? Like when you create a microscope, you actually have a completely different set of states that you observe, right? That you've never seen before, or even the first time you go on an airplane, right? And you look down into the ground. How do you behave on an airplane? Like you've never encountered those kinds of states before. So the ways that we make analogies to be able to generalize to those kinds of situations are going to be really key. And so non-parametricness is going to be a really important part of that. And the other thing I was going to mention, just to Avi's point, is that the other thing that I think is missing a little bit from a lot of the work that I do and that I think most people here do is multimodal kinds of inputs, not in terms of multiple modes necessarily, but being able to integrate sound and touch and language, right? Like our ability to communicate actually constrains a lot of the kinds of things that we do. And people who don't communicate might do different things, or the ways that we learn to communicate are all bundled up in the same kinds of timeframes that we learn how to act. There's actually a lot of really cool research on the connections between language and tool use, in particular in cognitive science and in comparative science. So I sort of think like non-parametric is maybe the most critical for being able to adapt to changing situations. But then, yeah, I'm also a big proponent of physics because physics is just true of the world. And so like we can build many things on top of physics. Physics, I think, is not enough to be able to do these things because there's lots of systems we don't actually, as humans, intuitively understand the physics of, and yet we can interact with them very flexibly. So we need to have dynamic notions of sort of how we can learn input state action mappings to like what's going to happen in the future.
Cool. There's definitely a lot more to unpack here, but I'm wondering if we can go to a question from the audience, if there are any. But I'm not sure if there's anyone.
There don't seem to be any questions from the audience here right now, but I think there was something on the chat. So I think it was
Yep, definitely. I mean, feel free to ask questions via Slido or raise your hand in person or on the chat. Otherwise, there's plenty of stuff we can talk about here, so we'll just keep going here. I think one related point that came up that Doina mentioned as well that I think is particularly interesting is the role of data versus priors as well. And so, as you said, Doina, data is a form of prior. You mentioned that even maybe the earlier works on entropy regularization to some sort of prior, that prior is still based on some experience in the past. So you're making an assumption of what domains those are and so on. So I think I'm curious about all of your thoughts on the role of data, both in an offline and an online context. So in an online context, how much should we rely on the prior itself? I guess that's very much the question, but what do you think is the right way to rely the right amount on priors? And in an offline context as well, if you have a bunch of data that you want to use somehow for transfer, are there particular, benefits to distilling it into a policy and using a kind of behavioral prior in that way? Maybe for that latter point, we can start with Avi.
I'm sorry, I missed what the latter point was there.
Oh, sorry, yeah. The latter point was just in terms of sort of thinking of data as a prior itself, and just in a representational capacity, what do you see as the benefits of working with data directly from offline data and like transferring it to the replay buffer or something, versus kind of representing it as a parametric or non-parametric or highly parametric policy that behavioral prior.
Yeah, I think the biggest benefit of working with data directly is that when you're trying to sort of like come up with some kind of a structure yourself, you are bounded by how smart you are. Like how many different cases you can sort of like account for when you're, let's say, like designing this inductive bias and so on and so forth. Versus when you're working with data, the only bottleneck that you run into is, let's say, the amount of data that you have and, like how diverse it is. And over a long period of time, I feel like the latter is sort of like a much higher ceiling to run into as compared to anything that you design based on your understanding of the world, because your understanding will always need to be updated at like a much more frequent rate. So, it's kind of like, what kind of ceiling do you run into? It's like, do you run into the ceiling of your understanding, or do you run into the ceiling of, let's say, like the complexity of the world itself? And it seems like the latter is a much higher ceiling, which is why I personally see, just using data as a prior as like more beneficial.
I think Nicholas has a comment.
I guess maybe 2 points to consider here. I guess, so you were talking about the inductive bias that your model brings with it, maybe as a negative, and in some ways it is, because once you form some abstraction, you can't necessarily undo that anymore, right? And I guess this is sort of what you're referring to, the capacity constraint. But at some point you will have to do it, and sort of maybe you can delay that step until later, sort of keep the data around. But at some point you will have to maybe think about what the relevant information is from the data. So you'll have to make the decision at some point. I think an argument maybe for not keeping just the pure data around could be a computational one, in the sense that processing the data at any point in time to extract some information or to make it usable for a certain purpose can be expensive. And when we sort of, I think so far we have had actually very little reason to worry about the compute constraints of our learning machines. But maybe as we move more towards towards larger scale scenarios, but also towards actually having robots that process something in the wild, this may become more of a consideration. And then abstractions of a certain type will be needed, not just for generalization during learning, but maybe also to enable adequately fast processing at test time.
Any of the other panelists have any thoughts on the role of data? Kelsey, I think, go ahead.
Yeah, so I think that role of data is very important. And I think something that is missing from this, though, is how do you actually get the data, right? Like, it's always coming from somewhere. And the way that that's limited is limited by the exploration of the people or the robots that created it, right? And so it's not just bounded by the complexity of the world. It's also bounded by the amount of world that is explored by the data gathered, like the data generating procedure. And in order to effectively explore the world, to get that good data, you might actually need something to constrain the directions that you explore, or like the ways in which you explore, which might come back to things like behavioral priors. I think that you're absolutely right that we are constrained by the kinds of behavioral priors we bake in. But so I think that like actually trying to think very critically about what things actually seem true of the world and bake only those bits in seems relatively promising to me. But yeah, I just wanted to add this dimension of we have to critically think about the data generating process itself as well.
I think my video seems to have gone, but hopefully you can still hear me okay. And I think what you were saying also ties into something Animesh mentioned in his talk of finding kind of, in my words, sort of causal invariances, right? And so finding what matters and what doesn't matter might be the form of prior to. I think Animesh, you were wanting to say something before. Maybe we can go to you.
It's less of a comment. It's actually more of a question, perhaps even rather incendiary. Is of course my belief is evolving as a researcher. I don't have like I believe in never say never, evidence-based beliefs. I used to believe that large-scale data was the primary driver. In fact, like I put my money where my mouth was, in the sense majority of my postdoc, I spent 3 years building infrastructure to collect the largest possible data set. At the time it was large, and then since then it has been done. But I think over the last 3.5 years, we have been working on causality, on looking at, I don't work on transformer models myself. We are users of transformer models at best. We increasingly come to the realization that it's not data versus priors or data, and it's like you need both. It's not an option. It's not like you can put a 3-layer MLP or a 20-layer MLP or a 1,000-layer MLP or whatever, like whatever fits in your largest sort of supercomputer you have, without any bias, right? Like it's not just the data, and the argument is that bias, and I think Avi did mention this, right? This is the part where we don't want to fall on the wrong side of putting in too much, but we want to find the right sort of principles of elemental components, if you will. And it's just not clear to me that we have that for sequential decision making broadly, robotics being one special case, but we just don't seem to have that for sequential decision making. Oh, did we lose Dushyant, I believe? So no adult supervision. But I would like to ask all of you, I think, what are your thoughts on this? Of course, it has been the case that the marginal value of adding data has been very high. And I completely agree with Avi, right? That the ceiling But it feels to me, and maybe it's more of an old school thought, that doesn't seem to just work always, right? We somehow are not able to do what you would say discrete reasoning. I don't want to use the word compositional because it can have many meanings. People can argue transformers do that. Almost all of the case, like even if you look at like large language models working, well, they work because the input is quite literally tokenized. So I'm curious about that. I don't know the answer to this. So this is like evolving philosophy.
I don't think I've followed the last part. Like they work because
So what I'm trying to ask, the question is basically, it seems to appear in the comments that we are making, it's as if data versus priors, but I'm of the argument it's not that. You cannot substitute data. That part I've come to agree to. Like, so scale in data is a requirement, it's not an option. However, just that will not do the trick. That is the argument that I have. If we agree to that argument, it's not necessary that you do, but if we do agree to that argument, then the question does come up, what else do we need aside from data?
I think Doina might have a follow-up.
Yeah, so I agree that data is essential. I think whether you need priors or not really depends on the circumstances of, can you gather the right data? Do you have, going back to something that Kelsey said, right? You might need the right behavior priors in order to gather the right data. And if you don't have the right data, then that's too bad. And similarly, perhaps there's trade-offs in terms of how much are you willing to wait to get the data and how much are you willing to spend compute budget and so on, right? Like using priors, and again, I think of priors as a very wide spectrum. Like some of them might be very strong and very informed by knowledge about the domain, and some of them might actually be pretty general and loose. But if you don't have enough data, or you want to do things quickly, or you want to do things safely or robustly or so on, you may need to put in something else and then scaffold off of that, I guess.
And that's also what I was trying to get to earlier. So even if we keep all the data around, at some point we want to make use of it. And at that point, we will be injecting some inductive bias with the model that we use to make use of the data. Could be a strong one or a weak one. I do think, but I think it just happens naturally. We can delay this and keep the data in its raw form around, but we will have to do it at that point. So I very much agree that it's not either or, it's both. And then maybe the question is of how strong the prior should be. And I think there the point about maybe what kind of data is available for us and how we intend to use the data becomes relevant. I guess much of what's happening at the moment with language and image models is that sort of expert data in a certain sense is already there. And this is sort of what they these models are based on. Now, if we imagine that our systems, maybe as robotic systems, have to act in the world, have to learn from the interaction with the world, and maybe the data that they have available is not expert in that sense, and they need to extrapolate from what they've seen so far. So maybe a different form of, or a stronger form of prior may be beneficial in this scenario, as Kelsey sort of was sort of saying earlier, for instance, to do efficient exploration. But I'm not sure. I certainly agree with your point, Animesh, that sort of spatial-temporal reasoning is something that perhaps in the robotics or RL community, I mean, it's been done a little bit, but not very much, I guess, again, because the tasks have been relatively easy and didn't require much of it. One thing I'm wondering about, I intuitively also agree with your comment about the capacity constraint model that kind of processes what's needed in a particular situation, as compared to processing everything or keeping like a complete state around. What I'm wondering about is people have been spending a lot of time learning, for instance, video models, right? That's been a big thing. I guess still is a big thing. And there, I'm wondering sort of whether the scenario there is different or the same that we are encountering. Maybe because the evaluation criterion is different. So I guess if you have to do video prediction, you inevitably have to kind of predict much of the world. Whereas if you're interacting, maybe you have a sort of more narrow, you can afford to have a more narrow understanding because you're acting in context and you have a particular sort of thing you want to achieve in the world. So I don't have an answer. I'm wondering sort of whether how these problems are related.
We have a question in the chat from Elena as well, suggesting that maybe priors are also a method of interpreting data. So perhaps this ties into what Avi was saying before, you know, there is maybe an upper bound on the kind of human interpretability or human understanding of this. And, you know, if we use raw data instead as a prior, rather than some sort of policy, then perhaps we can interpret what the data is via that policy and its behaviors as well. I don't know if anyone has any thoughts on that.
I mean, inevitably, when you make use of the data, I mean, even if you use basically a non-parametric model, you typically define some form of distance function, right, to look up similar data points, like in a Gaussian process or in a kernel density estimate. So there is, and that is some form of inductive bias or prior. So I think very naively, I would subscribe to that statement, sort of in that sense, at least. So I do think whenever we make use of data, we will apply some model implicitly, explicitly, and that is a form of inductive bias or prior as to what matters.
Maybe we can pause there and see if there are any other questions from the audience or in Zoom. Just put your hand up remotely.
I actually had a question. Well, I'm going to be part of the audience now, and I have a question. My question is basically related to, well, this conference on robotics. Basically, I have been walking around looking at all sorts of cool, crazy looking robots. And one thing that occurred to me is robotics is, especially with the hardware and sensing, it's a very quickly changing landscape. We have new robotic hardware and sensing technology, well, every year if we go to ICRA. So I was wondering, given that, so specifically for robotics, what do you think are, say, some of the most important priors that we need going forward, or what might be some of the pitfalls and the sorts of priors that we've been using?
Any of our panelists want to venture an answer?
I think lack of standardization with respect to hardware and sensing is probably one of the biggest reasons why it's so difficult to do data-driven robotics as opposed to, you know, data-driven NLP or computer vision and whatnot. And yeah, I mean, you know, you could adopt the approach that perhaps if you have, like, you know, rapidly changing hardware, that's even more reason to use models that are relatively minimal in the kind of assumption that they make about the data, and essentially just, you know, train one model to do everything, you know, kind of like the Gato paper that came out recently. And while things change every year, hopefully they don't completely change every year. So, you know, you can like sort of like still transfer knowledge from these like previous data sets using slightly outdated sensors and whatnot.
I wonder if this ties into the previous conversation on the form and structure of behavioral priors as well. Because it seems like one solution to this would be to find the right form of behavioral prior that's cross-embodiment, regardless of any low-level happenstance that might happen in the robot. You know, I can hand wave that away, and like that's usually the challenging part and the dirty part. But are there other ways that we can kind of incorporate prior experience across embodiments, rather than, for example, hierarchy or anything like that?
I mean, an obvious, I think, way of doing it, which is relevant to many scenarios, maybe not all, is sort of an understanding of the world around you, right? So that's maybe not behavioral prior in the very narrow sense, because it's not necessarily something that prescribes your behavior, but it will sort of, if you have a good understanding of the world around you, of the meaning of objects, of the affordances of physics, then no matter what your embodiment is, it will probably be hugely valuable. So in that sense, I think that is an obvious candidate for something that's somewhat invariant. I mean, up to a limit. I think I can do certain things well, others maybe can't do those things, or whatever. The way I interact with the world is different, and in the same way, the other way around in other cases. Over lunch, we had a conversation about the soccer players and whether we could use high-level strategies from human soccer players or from maybe simpler robots, and maybe, but it's not clear, because I don't know, just the speed with which they go across the pitch, or the speed with which they turn would be very different, and so sort of this abstract understanding may not fit anymore.
I think that also speaks to the nature of data and the task you use, because I guess the prize you'd get from 6-year-olds playing soccer is vastly different to professional players as well. We'll get a lot of running towards the ball behavior. I sense, Animesh, you might have some thoughts on that, perhaps, to put you on the spot.
I think I first want to say this. I have also come to the conclusion that affordance is not something that can be independent of the agent. I have a much simpler example. The way you open a door versus the baby opens the door versus the dog opens the door is very different, right? To a dog, handle is not a thing, because a handle it can never reach or use, right? So affordance is not, let's say, agent independent. Affordance is, I would argue, a property of object, function, and or object, task, and agent. So learning a large-scale prior independent embodiment would be very hard. Nonetheless, because many of our robots share embodiments. So even if, let's say, they are all 6-DoF robots, the kinematics may be slightly different. Regardless, the fact that the grippers are, let's say, parallel jaw or 3-fingered or 4-fingered, and the kinematics is kind of the same, if not exactly the same. There are mappings without holes, in a sense. You could learn these sort of priors. I think one thing that I would like to say, particularly in answer to the question from the audience member, was something that Kelsey mentioned is, if we are having good sensors, particularly, let's say, force, tactile sensors, one of the things that we don't have, and like this is an open question, perhaps someone will take this up for a challenge, is in the same way we are learning language and vision priors right now in the community, right? We are basically learning these DALI 2 style models joint. It would be very good to use large-scale pre-trained models of vision and touch, right? You know what grass feels like, or you know what a hot cup would feel like versus a gummy bear. Because having that prior a priori before actually acting would be very useful. You could argue that, yeah, it's like learning a model of the world, but it's more like learning the object-centric model of the world. I'm not learning how the world behaves in a global sense. It's more like in an object-centric sense, I know what perception or what percept to expect in my multimodal channels. And I think that I don't think we have that yet. People are trying that. I think there was a cool paper by Fei and Jiajun called Object Folder at Coral last year, and then I think this year as well at CPR, I believe, which was an initial attempt at this. But again, I think scale is a challenge in that space.
Okay, there's actually one question in the chat, but unfortunately we're at time. Maybe the panelists can have a look at that afterwards as well. But let's thank all the panelists for a great discussion. And I think next up we have Spotlight, so I'll hand back to the organizers.
And thank you to our moderator for moderating the panel as well, and to the organizers.
Thank you all. Thank you, Dushyant. And thank you to our organizers. I think this has been a wonderful workshop. I'm so sad that I've not been there, but hopefully sometime soon.
Thank you all.
Thank you.
Yes, thank you very much.